Hi everyone, and welcome to this second training of the INF⁴INiTY project. Today we are going to look at computationally efficient site-specific design load cases for the design of floating offshore wind turbines. You are going to be hosted by myself, Gael Verao Fernandez. I am the project coordinator and postdoctoral researcher in TU Braunschweig from Germany. And also Markel Peñalba, who is a lecturer in Mondragon University, and also is the work package. Well, is one of the work package leaders in our project, and is doing a lot of the numerical work. The session of today is going to last for 1 hour, and now I'm going to do a brief introduction of the project, where hopefully I will only take 5 minutes of your time, and then Markel will dive into the design load cases, and typically we will have 10 minutes at the end for questions. Of course, if there are a lot of questions, we are always happy to answer them and stay a bit more time. If you have any questions or any question pops up into your mind during the presentation, just feel free to put it on the chat, and then at the end of the presentation we will answer them. So I'm going to share my screen first. Apparently, oh, I shared the wrong window. 1 second. Yeah, normally now you should be seeing my presentation. So as I already mentioned, today is the second training. So basically, INF⁴INiTY, it's an European-funded project that stands for Integrated Designs for Future Floating Offshore Wind Farm Technologies. And it's a project that aims to develop nature-inclusive design solutions for floating offshore wind, both for the floating substructure and the gravity anchor. It's a consortium of 13 partners from 8 countries, and the objectives are very clear, but our two main objectives, or I would say the two main objectives, are to achieve a front-end engineering design for a floating offshore wind turbine with nature-inclusive designs, and also to perform a TRL5 validation of this design by means of large-scale modeling. So at the beginning of this project, we started with conceptualizations of what we wanted to achieve. So an initial gravity anchor design, an initial design for the floater, and then we established a methodology to obtain the final innovation designs. And this methodology consists on a design process for the two elements, both to the means of iteration via numerical simulation and experiments, and also everything goes through a framework of optimization of the innovations that we are creating. And also we need data sourcing for our numerical and experimental modelings. And this is where the seminar of today comes. So how we are defining the design load cases that we use as input parameters. So the case that our case study, or the boundary conditions for our design, is that we are trying to achieve at least a design that can hold a 12 megawatt turbine. Currently, we are making numerical simulations with a 15 megawatts turbine. And then we want our design to be feasible for the Mediterranean, Baltic, and Scottish seas. So in terms of gravity anchor, we have already designed or achieved 3 designs for the gravity anchors, that now we are studying how it is possible to integrate nature-inclusive designs in those. And we are going to release the design guidelines that we follow, so including all the standards and the design methodology that we followed at the end of this year, so in December 2025. And in parallel, we have also performed a study of the site areas, identifying the most relevant species at the bottom. So then to be able to know also the boundary conditions for the possible NIDs that we can integrate within our anchoring system. This will not be released at the end of this year, but at the end of the project, so in 2027. So the different designs conceptualizations that either we design or that we take from another designers, because there are also several concepts outside in the world. In terms of the floating substructure, so we started from the initial concept of the GCON floating structure, and after some iterations, we have finally achieved the 5th generation of the floater that can host a 15 megabytes turbine, and that is the one that we are now currently using for our numerical modeling and also for our TRL5 experimental validation. Again, all the standards and design methodology will be delivered at the end of the year, so at December 2025 in our design guidelines. Similar to the anchor, we have identified the different species on the 3 study sites that we have, so the Scottish, Baltic, and Adriatic seas. And now we are in the process of designing the nature, so the artificial reef structures that we can embed within this floater, and that will help us to mitigate the impact that having this floater out in the ocean will have. So for that, we are performing numerical modeling. So we are at the moment doing hydrodynamic analysis of the existing floater design and the existing mooring configuration. And specifically, we need to look at the operational loads to assess the fatigue. And also we need to look at the DLC's standards, because we are also looking for a standardization or certification of the turbine that we are designing. And for that matter, we have designed a GUI that allows us to retrieve these design load conditions or these operational loads in the locations that we might choose for installation in the North Sea, the Baltic Sea, and the Adriatic Sea. And this is what we will have a look today. So this is how the GUI looks like. And if you are interested in downloading the GUI, you can find they are hosted here in our Leopard repository. So you can just click on this link and access the GUI and play with it yourself when the seminar is finished. So thanks a lot for your attention. And with further ado, I will let Markel to give you an introduction on the GUI and he will show you how to use it.
All right. So let me know if you can hear me correctly and you can see my screen. You should be able to see my screen now. Is that correct, Gael? Yeah, perfect. Okay, so thanks, Gael, for the introduction and the presentation of the overall project, of the INF⁴INiTY project. My name is Markel Penalba. As Gael said, I'm a lecturer and researcher at Mondragon University and also Basque Foundation of Science. And I will present today the computationally efficient site-specific design load cases for the design of floating offshore wind turbines of the future. So basically, we will go through the different stages of site characterization, definition, and selection of the design load cases, and then an example. I'll show you now the outline. But in the next 45 minutes, I will show you the different aspects we've been analyzing in the last few months within the INF⁴INiTY project. And we will finish with a couple of examples using the graphical user interface Gael was mentioning. And the one you can download from the Leopard repository, as Gael mentioned as well. So the let me see if I can switch the slide. So the outline of the presentation is the brief introduction about the project, and specifically the work package 5, which is the one where we developed all these aspects, context and the motivation of designing and selecting a reduced set of design load cases, the presentation of the site-specific database, and we will go through some historical data, future forecasts under different climate change scenarios, and also the definition of the DLCs, design load cases, a little bit about the reduction techniques and specifically clustering techniques we've been developing and using to reduce the amount of the environmental conditions that are necessary for the analysis of the different designs. And finally, as I was mentioning, a very brief case study with 2 or 3 examples using the graphical user interface we developed, and it's available, openly available. And I will conclude the presentation of the webinar with some conclusions. As the guy said, you can write the questions in the chat, or you can afterwards at the end of the presentation ask your questions, or obviously feel free to send me an email or send Gael an email with your questions for further information. So as I was mentioning, the introduction of the Work Package 5 and the work I will be presenting today. The Work Package 5 is focused on the farm scale modeling. So basically we are developing together with DTU, who are the leaders of this work package, NIDAS, GCON, Hanover University, Ghent University, Politecnico, and Politecnico di Torino, and Technical University Braunschweig. We are developing the models at the farm scale. So basically the main objectives are, first of all, the characterization and dissemination of the design load cases, which is what we are focused on today, the aerodynamic modeling of the floating wind turbines using high fidelity CFD simulations, also farm scale CFD simulations, in order to optimize the layout based on basically the annual energy production in this case, which in Work Package 7 evolves towards the techno-economic or even techno-environnomic optimization, including economic aspects, environmental aspects, and social aspects. But I guess this one will be disseminated later in the project with a new webinar. So as I said, we will focus on the characterization and dissemination of the design load cases, including current and future conditions, resource conditions. And by current and future, what I mean is that we will characterize the 3 areas of study that Gael presented or Gael introduced: the Adriatic Sea, the Scottish Sea, and the Baltic Sea. So we will characterize it based on the past or historical dataset, which is the most common thing. Basically consider 10, 20, 50, or 100 years from the past and characterize wind, wave, current, sea level, etc., characteristics of the different areas. But we can also do the same thing by analyzing the evolution of the resource. And that evolution of the resource is not expected to be static, but is expected to change significantly under specific scenarios, basically because of the effect of the climate change. So as climate change hits harder or slower, we will see the resource, the wind and wave resource, essentially change significantly in some areas. And for that analysis, we will consider we have considered 3 different horizons: near term, which goes up to 2030, mid-term up to 2050, and then long term up to 2100. So basically at the end of the century. But not only different horizons, we've also considered different climate change scenarios and basically carbon emission scenarios. So we've considered the business as usual scenario, where we continue emitting the same amount of carbon emissions in the next decades. And that one is the scenario that will have the largest impact. But we have also considered another scenario where there is a mitigation of these emissions, right? So we will show, you will find in the repository, you will find information both about the resource characteristics, but also the definition of the design load conditions based on past and future scenarios under different horizons and carbon emission scenarios. And then what we will analyze as well will be the reduction technique, the clustering technique. So basically, once we have defined the wave and wind climates, we will try to identify the characteristic or the representative conditions, including wave, wind, current, and sea level, for example, the characteristic or the representative characteristics that somehow represent the whole area of study. And then once we have those representative conditions, we will analyze the accuracy of using only those representative conditions in terms of environmental-based condition metrics. So basically analyzing the resource itself, and also damage-based metrics, which will be focused on the fatigue analysis, and more specifically, as I will explain later, in the design load condition 1.2. And I will explain now why this design load case 1.2 and the fatigue analysis is particularly interesting for this sort of analysis. So the context and the motivation is that right now there is a major challenge when we design our technologies, and that major challenge is the need for analyzing or evaluating our technology under the whole operational region, which for the case of the floating wind includes waves, winds, currents, and sea levels at least, right? So the combination of all the different potential wave, wind, current, and sea level conditions, it leads to a huge amount of different conditions to be analyzed, and therefore it leads to a huge amount of simulations that need to be carried out in order to evaluate the performance or the survivability or the reliability of the system that we are designing. So to that end, what we usually do, and this is based on different standards, but the most common ones are the DNV and the IEC standards that I've shown here. They divide it into different conditions or different cases. Ultimate loads, which is more related to the extreme environments, fatigue loads, which is related to the operational environment, serviceability loads, so conditions where we have to perform some services, and then accidental loads, which are also maybe not that common, but at least present throughout the whole lifetime of the wind farms. So I have only included a picture of 7 different design load case scenarios for the power production region, right? So from 1.1 to 1.6, there are different wind and wave directionality, sea currents, water level, and even other conditions that need to be analyzed. But in each of these design load cases, the combination of the different potential conditions results in a huge amount of required simulations, and especially the fatigue analysis is the one that includes the most number of different combinations of the environmental conditions. And that's why we will be focusing on how to reduce this amount of simulations that are required for the fatigue analysis of the different systems we are designing or analyzing. So fatigue analysis is particularly demanding because it involves the modeling of joint probability distributions of the different metocean variables. As I said, waves, winds, and current. You will see afterwards that current is sometimes neglected, and even the standards, and not only the standards, even other white papers or reference documents suggest to neglect the effect of the current when analyzing fatigue loads. But this involves performing thousands of simulations. And when I say thousands, if you combine all the different possible scenario or possible conditions, wave, wind, current, then it results in tens or hundreds of thousands of simulations, which is unfeasible or prohibited in terms of computational cost. So that's why there is a huge relevance in reducing the number of simulations we need to cover the whole operational region or the whole operational region of the systems. So some guidelines, they already, and for the DLCs, they already suggest that what we need for the DLC 1.2, the fatigue analysis, we need to cover the whole wind operational wind conditions from the cut in to the cut out, all the marine conditions, including weights that suggest the normal sea state joint probabilities, so significant wave heights, peak periods, and even wind, right? So we need to combine all the different possibilities of each of these values. Sea currents, as I said earlier, they can be negligible in some aspects, and some standards actually suggest to neglect current in this fatigue analysis. And we also need to analyze the mean sea level as the water level changes. And you will see that this is one of the factors that, for example, changes with climate change. And then we also need to analyze wind and wave directionality, both misalignment and also the multidirectional aspects, right? So we need to analyze both cases, which adds on the original set of different conditions. So it's not only wave height, peak period, and the wind speed, but also the different wave and wind directions that each of these combinations require. So if that's the set of different the environmental conditions, then we also have to run time domain simulations. And some of the white papers or the reference standards, they suggest that about 5,400 seconds of simulations with 1,800 seconds of transients that will be deleted afterwards or neglected afterwards are required. But not only for each of these combinations, and also 6 wind and wave seeds. So that leads to, as I said, tens and hundreds of thousands of possible combinations that we need to analyze with our time domain simulations. Considering that each of these time domain simulations runs quicker than real time or similar to real time, it means a lot of different combinations and therefore a lot of computational cost and time. So this is something that different people, different studies, different standards have identified already. So different studies have suggested different tricks to reduce this computational effort. And actually the Life 50 Plus project, which is one of the reference projects we've been considering, but not only us, the literature also considers, they already mentioned back in 2018 that the selection of a reduced set of critical conditions is very valuable, so that we can limit the final design load cases table set, so the different conditions, combinations of the environmental conditions. So you will see in the literature that some reference studies, they simply analyze a set of very, very reduced number of conditions. You see the static conditions, the parked operational conditions, but also operating conditions, where you only see 7 different operational environmental conditions with different wave and wind conditions. So this would be reducing from tens to hundreds of different thousands of simulations to only 7 combinations of the conditions, which is a huge reduction, but it may not be sufficient. Some other projects like the Life 50 Plus project, they suggest about 3,000 different combinations, combining wind speed, combining wind direction, wind seeds, wave height, wave period, and also wave seeds and directions. So having about 4,600 seconds of simulation in each of the combinations, then it is a considerable amount of time, but we are still not sure whether these 3,000 different combinations are sufficient or not. It is evident that there is a huge reduction from the tens of hundreds of thousands of different combinations. And one of the final references I found in the literature is the IEA Task 49 reference paper, where they defined the cluster techniques as one of the potential techniques to systematically reduce this computational effort. But they suggest that combination of wind and wave conditions of about 100 Metosian beans, so 100 of different combinations, might be sufficient. So based on these 3 different reduction tricks, what we are somehow lacking is a consistency and a systematic approach to actually reduce this DLC table set that was analyzed or that was mentioned in the Life 50 Plus deliverable. So that's what we are looking at today. Not only the definition of or selection of the DLCs that we need to analyze in our design, during our design, but also the definition of the different environmental conditions through a systematic approach that provides the final number of environmental conditions that are required for the design. So we suggest clustering techniques as the IEA Task 49 reference paper suggests. And what is a clustering technique? So clustering technique, and I will go deeper afterwards, but clustering technique essentially is grouping the different environmental conditions. So if we have 2 dimensions and we have all these green points, combining the 2 variables, we can group them in 3 different groups of conditions. So we assume that each of these groups has the same characteristics, and therefore by defining the centroid of this group, we can define the representative conditions that represents the whole group with a single point. But again, even if clustering techniques have been suggested for different approaches and different applications in the last decades or years, the literature shows no consistency on the use of these clustering techniques, and especially on the use of the number of clusters, so that we can somehow define as the IEA document that with 100 or 1,000 or 5,000 or 10,000 different clusters. So this is what we are looking at today, and we've been looking at the last few months within the INF⁴INiTY project. So as I said, the overall methodology, basically, we will define the site-specific resource information, resource characteristics in terms of waves, in terms of wind, in terms of current, sea level, and so on. Once we have defined this site-specific data, and we will focus, as Gael mentioned at the beginning, we will focus on the 3 areas of study we defined at the beginning of the project. Once we have this site-specific Metocean data, then we will try to analyze the clustering techniques. So we will analyze different clustering techniques. We will select the clustering technique we want and define the centroids that represent the different groups that have been divided into the Metocean conditions of each specific location. And then, as I mentioned earlier, we will have environmental-based metrics. So basically, only using aspects like wave height or wind speed, but also design-specific damage-based metrics, which will be based on the fatigue analysis, right? So we will analyze the centroids, we will get the tension signals for the centroids, and then once we have the tension signals, we will analyze the damage and the lifetime corresponding to, in this case, the mooring lines of the system. So let's focus on the site-specific database. So we will, as I said, 3 areas of study: Scottish Sea, the Baltic Sea, and the Adriatic Sea. You will find all the information based on for the historical data set in this Leopard repository. You can click on this link and you will go through to the Leopard repository, where you can download both the original version of the graphical user interface and the whole data set corresponding to the 3 areas for the historical data set. And we've also defined some technology requirements so that we can reduce the areas to the really interesting locations where the deployment of the wind farm, and specifically the wind farm based on the GCON 15 megawatt turbine, would be potentially interesting. So we've defined a minimum and a maximum bathymetry. We've defined the soil conditions where we can't actually or don't want to deploy the wind farm, so no rock, no boulders, no coarse-grained sediments, and a minimum annual average wind speed. So for the Adriatic Sea, that minimum corresponds to the 6.5 meters per second. The Baltic Sea is 9.5 meters per second, and the Scottish Sea, the minimum would be 10 meters per second. So we will filter the whole areas with these conditions and identify the locations, the exact locations where these conditions are fulfilled. Also, especially in the Baltic Sea, we've considered ice thickness. So if at any point during the year we have an ice thickness of over 0.2 meters, then we consider that that location or that site or that area is not adequate for the deployment of the wind farm. So historical data, I will go very quickly through the 3 areas. As I said, the bathymetry, you see the red points, they identify the locations that fulfill all the different requirements, right? For the Scottish Sea, you can see here the red points that fulfill all the conditions, and here you see the bathymetry of the area. Here is the annual mean wind speed, and again you see the red points where the conditions are fulfilled, and finally the soil conditions, so the soil characteristics in the area of analysis in the Scottish Sea, and again the red points where all the conditions are fulfilled. Same thing is analyzed for the Baltic Sea, and you see that the conditions are fulfilled in a much reduced area or number of locations, right? So you see the red points here. If I go a little bit back, you see the red points here as well. And finally, red points are also here, right? So, and if I can go, forward, then the same analysis for the Adriatic Sea. And here again, the number of points where the conditions are fulfilled is even more scarce in a sense, right? So you've got some points that fulfill the conditions of bathymetry, conditions of the mean annual wind speed, and the soil characteristics in the Adriatic Sea. So once we have filtered all these locations in the 3 areas of study, we have the original or the baseline data set for the historical data. But as I said, we're not only focusing on the past, we are also focusing on the future and the potential scenarios where the future resource can vary significantly. So you've got on your left-hand side, you've got the wind speed data, and your right-hand side, you've got the wave height data. So you've got the historical baseline. It is the same for wind and wave, the same we showed earlier. And you've got 3 different scenarios, near, mid, and long term. Remember, near term means 2030 horizon, mid-term means 2050 horizon, and the long term means 2100 horizon. And same thing for the wave scenario, except that in the wind case, in the wind analysis, wind speed analysis, you've got the conservative scenario where the emissions will be reduced and the business as usual scenario where the emissions will be exactly the same, right? So we can see it's all given in relative terms. So we can see that there will be areas where wind speed and waves will increase, but also where wind speed and waves will decrease. And actually, this is all mean wind speed and mean wave height. And you see the mean wave height is expected to reduce almost all over the European waters. While the wind speed, there are areas where wind speed is expected to increase, especially in the southern areas of the European basins. So based on this analysis, we have also identified and characterized the future scenarios for the Scottish Sea. And here, for the theories of study. So here I will show you the characteristics of some specific locations throughout the different horizons that we analyze under the impact of climate change for the business as usual scenario. So the more damaging scenario with the highest emissions. So the first conclusion is that the selection of the locations, so the filtering we've performed with the historical data doesn't change at all. So we keep having the same filtered locations within each of the areas, but the wave and wind resources do vary, right? So Scottish Sea, for example, if we analyze, and I focused on the 59 north, 2 degrees east, so 59 degrees north, 2 degrees east location in the northeast of Scotland, so that I can show you the wave conditions in the scatter diagram. So you see where the maximum occurrence happens at peak periods of between 6 and 7 seconds, and about 1.5 meters. But if we go farther in time, we see that there are some increases. So basically, the maximum, the most occurrent points are decreasing a little bit. Same thing here. But the maximum areas where the extreme conditions, the limits of this scatter diagram are extending towards higher and longer waves. And that's what you see here in the baseline 2050 and 2100. And same thing for the wind speed. So wind speed, you see the tails increasing a little bit towards the higher wind speed values, but the mean, so the peak of the wave distribution, or the peak of the wave distribution in this case, it's getting towards the left a little bit. So basically the conclusion, and same thing happens in the Adriatic Sea. So you see the core of the wave conditions decreasing both in period and wave height, period and wave height, but the maximum extreme events increasing towards higher and longer waves. And same thing happens in the wind resource for the Adriatic Sea. So basically what is happening or what we expect in the future under the business as usual scenario, at least, is a decrease of the energy potential in terms of wind and waves, so decrease of wind speed and wave heights, but an increase of the extreme events, both in frequency and the power. So more and more powerful waves and wind speeds will appear in the future within the or under the business as usual carbon emission scenarios. So once we have characterized the site-specific database for the definition of the design load cases, and also for the use or the description or the definition of the graphical user interface, we've selected 4 different power production design load cases, one power production plus faulty condition, and 2 parked conditions. So 1.1, 1.2, 1.4, and 1.6 for the power production region of power production conditions, 2.3 for the power production with faults, and 6.1 and 6.2 for the parked conditions. But in each of these design load cases, we need to define wind, waves, and all the combinations between them. So as I said earlier, we will design describe all the design conditions, all these design conditions for each of the filtered points within each areas of study. And we will define all the different wind and wave combinations that are potentially expected to happen in the both historical and future scenarios. So as you can see here in the fatigue analysis design load case, so the 1.2, we do need to consider misalignments and also multidirectional cases, but sea currents are somehow neglected, as suggested earlier and also suggested in different standard guidelines and white papers. So I will focus on the design load case 1.2 and specifically now describe the clustering techniques we've been using or developing in this INFINITY project. So basically, as I said earlier, the clustering techniques, they reduce the number of different or methodology conditions, combinations, 3 variables, 2 variables, depending on the amount of variables we want to analyze. And they group all these variables into clusters and define the centroids of the clusters that represent the whole conditions within each cluster. But as I said, there is different examples in the literature, but no consistency in the methods or no consistency in the required number of clusters. So this is what we need to analyze to suggest a number of the specific method or a number of clusters. And 2 more, drawbacks of the literature are that we only found analysis in resource specific or resource environmental based metrics, right? So you're only using wave heights or wind speeds, but nothing about the design parameters we need to use in the design process, like fatigue, like power production, like downtime, like weather window definition, and so on. So it's only resource-specific analysis, and this is something we addressed in the recent publication in the OMAE conference, OMAE 2025 conference in Vancouver. And the second drawback or second lack in the gap in the literature is the use of only past or historic methodology conditions. So also in this project, we've been looking at the definition of design load cases based on future design conditions, and this is also something we addressed in a recent presentation in the European Wave and Tidal conference, and some of the results I will be showing them today to you in this webinar. So first of all, clustering methods. There is a classification of different methods. As I said, the clustering techniques are not something that are new. They have been there for years or decades now, and they have been applied into different sort of applications, but including resource assessment. But they've always been applied to environmental conditions only, and there is no consistency on the results showed by different people. We have studies that suggest that to use only 20 clusters, to use only 100 clusters, but others suggest to use up to 5,000 different number of clusters, right? So in any case, we've got different algorithms we can use based on the partitioning, like using k-means, for example, which would be the more representative technique within this methodology. Hierarchical algorithms somehow, like the agglomerative or the Birch techniques, the density-based, like D-scans, grid-based, like the wave clusters or Sting, or model-based algorithms that can be used for the definition of the clusters and the centroids, right? In our case, we've performed some sort of benchmarking study. And for the benchmarking study, we've defined different evaluation metrics. So the first of all, and probably the one that is most commonly used is the quality metric. So basically defining the distance, the geometric distance of the cluster centroids and all the different conditions within each cluster, so that the quality measure increases as that distance decreases. So therefore, increasing the number of clusters will decrease significantly the number of the quality metric. So what we want is a quality metric that is close to 1 or 100, depending on how we normalize it. But also people have used different performance evaluation metrics like 19th percentile error in power production conditions. So representing the power production conditions, 99th percentile error representing the extreme or the survivability conditions, and also probability density function score, so PDF score, where not only a single average or mean value is considered for the evaluation of the bias or of the discrepancies, but the whole probability density function of the data set is used, so that the two probability density functions, the original and the one based on the clusters, are compared and see where the gap is. So basically the areas of the probability density functions are compared to compute this PDF score. And finally, some damage-based metrics. So basically metrics that are not purely based on environmental conditions, but on the design parameters. And in this case, as we are looking at the fatigue, we analyze this fatigue analysis or fatigue damage based on some spectral analysis. I included here a couple of publications where we have developed this spectral fatigue assessment methodologies, including mean stress, which is important in the specific application like moorings, for example. And you will find in these links, you will find all the codes required to compute this spectral fatigue assessment methods, instead of using the more common and more computationally expensive frame flow counting technique, the time domain technique. So basically what we do is we extract the tension time series tension results of, in this case, the mooring lines, but it could be any other component for the different environmental conditions we want to analyze, either with or without clustering techniques. And then we define the DMV standard procedure, defines SN curve that is based on the 20% mean stress load, while what we want in our adaptation of this process is to use mean stress correction, so that we can correct the fatigue analysis to the specific mean stress that is applied in the different tension conditions or environmental conditions. So this is computed already using the Minus rule, so that we can extract the accumulated damage with fatigue. And we've run this benchmarking procedure where we identify the FOW method as the one that provides the best accuracy, but they want even beyond, or even improving the results provided by the dual narrowband method that is usually suggested in the, for example, DMV standard, right? So now we can perform the benchmarking, and we've used 4 different methods: the k-means, the agglomerative, the Birch, and the maximum dissimilarity algorithm. The ones that have been used usually especially in the resource assessment or wave resource assessment areas, and also multiple variables. So 2 variables, which could be, for example, wave height and wind speed, 3 variables, wind speed, wave height, and wave period, and 5 variables, wind speed, wind direction, wave height, wave period, and wave direction. So you will see that independently or regardless of the technique we use, increasing the number of variables decreases the quality measure, because reducing this geometric distance is harder and harder as we add new variables. But at the same time, we can see that all the algorithm converge somehow close to the 1,000 number of clusters. 1,000 number of clusters right here. I thought I had this highlight, but there is nothing. So yeah, around this 1,000 number of clusters, we can see that 2, 3, or 5 different variables, the results, the quality measure somehow converges to the close to the highest value. So based on these results, we could say, first of all, that the k-means is the in all the different sort of variables or number of variables, k-means is the one that is most efficient. So it requires the least number of clusters to achieve the highest quality measures. But at the same time, we can conclude that 1,000 number of clusters might be sufficient to convert this statistical analysis of the site-specific environmental conditions, regardless of the number of variables we use. However, this is only based on the environmental conditions, and in terms of analyzing these results against some other publications in the literatures, for example, the one suggested by Kanner and their colleagues in the OMAE 2018, we can compare the same analysis, and we can see the k-means is way more efficient, or way more accurate, because with a relatively low number of clusters, we can achieve the same results as obtained with the maximum dissimilarity algorithm for a significantly higher number of clusters, up to 2,000 number of clusters. But at the same time, we can achieve over 99% quality measures with about 600 number of clusters. Although, as I mentioned earlier, the convergence seems to arrive at around 1,000 number of clusters, which surprisingly is the same in the case of the maximum dissimilarity algorithm suggested by Kanner and their colleagues. So if we go beyond the usual quality measure, we have the 90th percentile, and again, convergence reaches at about 1,000 number of clusters. The 99th percentile, even earlier than that, even though you can see that the the error or the bias is significantly higher for reduced number of clusters, right? Where we have a range of 0 to 7%. Here the range goes from 0 to almost 60%, right? So with extreme events, 99th percentile, the range is much larger, which is to be expected. But again, we have the PDF score, the third measure that or metric that, as you see, around 100 or 1,000 simulations seems to converge at 0.67, sorry, and only increases 3 points when multiplying by 5 the number of clusters. So again, this 1,000 number of clusters seems to be the consistent number of clusters that leads to the convergence of the different analyses. But if we do the same analysis for the damage-based historical data, so basically not based on pure environmental conditions or geometrical distances based on environmental conditions, but the fatigue damage, we can see that again, the 1,000 number of clusters appears as the convergence point for the analysis. And we've done the same thing with future data, where again, this 1,000 number appears as the convergence point. Even with lower values, probably would be sufficient, like about 600 clusters. But one more conclusion we can extract from this figure is that the longer horizons, where the resource is supposed to vary the most, the damage itself reduces. And that's because, as I said earlier, the average resource, the average wind, average wave, is expected to reduce under climate change, while the extremes are expected to increase. But the fatigue damage is purely focused on the operational region, the region where the average is the most representative, and therefore, if the average reduces, the damage itself due to fatigue is expected to reduce under the impact of climate change. So now we can actually go to analyze the examples, and I will switch. I will define now the example that I will be using for the use of the graphical user interface. As I said, this is something we can download from the Leopard repository. You will find something that is similar to this screenshot here, where you can insert the coordinates. You can select the either historical or future periods, and in the future periods, the scenarios you want to, the climate change scenario, excuse me, you want to analyze the exact range of the period you want to analyze and the characteristics of the turbine. This is slightly different in the latest version because we introduced the turbine characteristics in an Excel file that I will show you right now. And finally, you can select as well if you want or not to reduce or to define the reduced set of environmental conditions for the design load case 1.2. And finally, all you need to do is select the directory of the folders where you want to save the information. And this is the structure of the data set. So we've got input data. As I said, input data is the site characterization for the historical and future under different scenarios. So you will find the hourly information of the waves, the winds, the currents, the surface, the sea level, and so on. And the outputs provide, first of all, statistical analysis or reports on the statistical characteristics of each site you select, and also an Excel file or a CSV file with all the definition of the DLC conditions, including, if you select so, the reduced set of environmental conditions with the number of clusters you decide to select. So the example I'm running in this webinar is the GCON 15 megawatt TLP turbine with the conditions or the characteristics you've got right here. This is the default example you will find in the graphical user interface when you download it from the website. We apply it to a specific location in North Sea where we believe it's one of the very interesting locations to deploy the farm of floating offshore wind turbines. And then we will analyze historical period and also a future period under different scenarios, right? So 3 case studies, 1 full design load cases, so no reduction using clustering techniques based on historical environmental conditions. The reduced DLCs with 100 clusters so that it doesn't take too long, right? And to compute all these scenarios based also on historical environmental conditions, and finally a set of future environmental conditions. So if you let me switch my screen, and please, I hope you can actually, oh, maybe I actually need to switch my screen so that you can actually see. Now you should be able to see the conditions, the GUI itself. As I said, the coordinates, the period you want to select, the selection of the reduction using clustering techniques or not, and the repository direction. So basically, you will find a folder like this, where you have the Excel file that defines the conditions of the turbine, the diameter, the height, the rated wind speed, the cut-in wind speed and cut-out wind speed, and also all the natural periods of the floater, which are required for the definition of specific design load cases. And then if you double click on the executable, you will open this executable here. So if we define 59 degrees and minus north, minus 2 degrees east, and then I can select historical period. I can select 2018, 2020. I will select a very short area of, period, and then also copy the directory where the executable is. I hit calculate. It asks you to double check whether the turbine conditions are the ones you want. We click OK, and it loads first of all, methodology data, and second, generates the design load case condition. So if you go back to the input, you will see historical, Scottish Sea, and there is all sort of filtered locations here. 59 north to east is one of them, and you have all the information classified in different variables and years. If now I can go back to the output folder, here historical is the one we selected. You've got the DLC CSV files with all the design load cases defined, all the different figures that can be generated in terms of scatter diagrams and so on, and also automatic reporting of the statistical characteristics of the selected site. Now you see that it has been generated. So if I go Scottish C 59 and 2, I've got the full version. I open the full version. And if I, and here, oops, sorry, this is not the one I wanted. This is the one I wanted. You've got your Metocean data. You've got the DLC 1.1, all the conditions, DLC 1.2 with the misalignment, DLC 1.2 with the multi-directional analysis. Here, these ones are the full analysis, so they don't have any reduction in using clustering techniques. There is a standard reduction technique that basically selects the most occurrent wave height and period for each wind speed, right? And the probability that corresponds to it. But it doesn't have the clustering reduction, right? And then you've got the 1.4, 1.6, 2.3, 6.1, 6.2, and also the extremes, environmental contours, right? While if we do select the number of clusters, like 100, and calculate it, again, we can say, okay, yeah, these are the conditions we want for the characteristics we want for the turbine. It will generate the Excel file, exactly the same Excel file, but with the clustering reduction sheet where you can find the environmental conditions, the 100 environmental conditions, just because we found or we defined 100 clusters, right? So if I go back, and maybe I should let it load all the conditions. And yeah, doesn't take too long, but it takes a little bit to compute. So load all the environmental conditions, compute the DLCs, and extract the clustered combinations of wave wind conditions. So it should be relatively quick now. So otherwise I can show you. So what I can do is I can actually show you the results here. And so these are the conditions, that wave conditions. These results come from the statistical analysis report. So wind conditions, wave wind directional analysis, and the environmental contours extreme, identification of the extreme events, and so on. If we do the reduced case, you see here that there is one more sheet where you can find the 1.2 design load case with the clustering and all the information related to the clustering technique, even including the distance to the centroid and so on. And finally, you will have the same analysis. And if I can show you, yeah, it's now over. So this one should show the clusters I was showing earlier in the slide, right? So you've got your 100 clusters with all sort of characteristics, including the H's, so the wind speed, the wave height, the wave period, the distance to the centroid, the probabilities, and so on. And finally, you can also select the future period. You can select that one as the scenario, and then select any horizon you want. So last year, it should be like this one, for example, and this one here should also run the future scenario characteristics and design load cases. So I'll go back to the slide where you can compare the statistical analysis, and you can see that there are significant differences, or there can be at least significant differences in wind speed, wind direction for the final analysis comparing historical and future datasets. Same thing for the wave heights and wave periods. Like you see how the most occurrent point is moving slightly. Wave directions are also moving. Wind wave misalignments are also showing some displacement, some modifications, some variation, and same thing for the environmental contours, right? So finally, and I'm sorry about the delay, but finally, the conclusions. So basically, the INF⁴INiTY Work Package 5 has produced the site-specific Methodian database for the Adriatic, Scottish, and Baltic seas, with historical datasets and also future datasets with 3 different horizons, 2030, 2050, 2100, and 2 emission scenarios. The conservative one with the carbon emission reductions, and the business as usual one with the with the same level of carbon emissions up to 2100. Then also efficient load case, design load case definition and generation for the selection of the design load cases, selection of a reduced set of environmental conditions for the fatigue design load case, and environmental and damage-based sensitivity analysis. So not only purely environmental, but also the impact of defining one number or another number of clusters, for example. And all this is integrated into a user-friendly graphical user interface that you can find in the Leopard repository. And finally, more technical conclusions. The K-means seems to be the most accurate and most efficient clustering technique. It is comparable or better in terms of quality. It's simpler for its implementation, and its scalability for larger Methodian datasets is also more adequate. It also identifies or reduced but representative Methodian bins, fatigue bins, where 1000 clusters seems to be the number where the different results or different metrics converge. Accuracy is maintained in fatigue prediction. So if we use 1000 clusters, or we use 70,000 clusters, which is the maximum number of different combinations we've used in our analysis, and therefore we can achieve a massive reduction in computational costs, demonstrating that these 1000 clusters are sufficient for both Methodian characterization and, for example, fatigue analysis. So you will find some references in the presentations once we share this, and also the links where you can find all the information, including the Leopard repositories for the site-specific design load cases based on the historical data and based on future data with all the design load case generator graphical user interface. So thank you very much for your attention. Sorry again for the delay. And now I'm happy to answer any questions related to the webinar presentations, that said, whatever. Thank you very much.
Thanks a lot, Markel, for a very nice presentation. So indeed, now it's time for questions, if any. So you can write them on the chat. Yeah. So Berguthar wants to know what was the number of DLCs before reducing it to 1000 clusters on the example that you showed.
Yeah, that's a very good question. So the number of combination of environmental conditions, it depends on how you define it. Like, we haven't found any, like, as I shared the very beginning of the presentation, I think it was, there are different tricks that have been used in the literature, but no one actually says how many you need to use. The experience with different companies going through the certification process suggests that for the pre-FEED, about 70,000 different simulations are required by the certification bodies, while for the FEED certification, about 150,000 different number of combinations, environmental conditions are required. But yeah, you see here, the Live 50 Plus suggests 3,000. IEA suggests 100. Some people in their scientific journal papers, they use like 4, 10, 15 different case studies. So there isn't any fixed number of environmental conditions or condition combinations that need to be used, but it is well beyond this 1,000 or even 5,000. Like, we're talking about 50,000, 70,000, 100,000 different combinations. And if you were referring to the analysis we've performed here, we've gone. So these ones here, for example, we've gone up to 5,000 here, but we've gone up to 70,000 different simulations with the spectral fatigue analysis, and also another reduction technique when generating the tension time series. So we've gone up to 70,000 different simulations, and we don't see much of improvement in these groups here, or these curves where it is based on the fatigue damage. You are muted, Gael.
Sorry, thanks. Thanks a lot for the answer, Markel. I don't know if there are any more questions. If not, since we are already 5 minutes over time, I would say we leave it here. But as Markel mentioned, if you send us an email, we are very happy to answer you afterwards if it's a question about the project itself or the DLC GUI. And also we will, as Markel mentioned, we will share the presentation with you in case you want to have a better or a more insightful look at the equations and the methodology followed. So thanks a lot for attending, and see you on the next training that we will share also in our LinkedIn and our project webpage. So have a nice week. Bye-bye.
Yeah, thank you very much.